And that is cleaning and pre-treatment methods of the dry type. So we will have a quick glance of these methods. So we will look at laser, plasma treatment, flame treatment, CO2 cleaning, blasting, and steam cleaning. If that is dry or not, we can discuss. Maybe that's, but it's not the process baths. And we will compare it to more the traditional cleaning steps or pre-treatment steps in baths, where you normally use then water or solvent, and sometimes also chemicals, of course. But that we will not have a look at here. So the idea today is to have a quick glance of the dry methods, and the next step then is to go home and dig into the different topics then further on. And we at RISE we have worked more or less with these methods. For some of them, we have our own equipment and have done a lot of research and activities, and some of them are not. We're not so familiar with in practice, so to say. But yeah, the big advantage then of dry methods then is that you don't need to use chemicals or solvents, and in that perspective, you save. Or you have an better sustainability aspects of that. Some of them are also you can use as post-process. I mean, if you want to take away a coating, so to say, you can use them for that, and then you have the circular thinking of that to be able to use the product again if you delete the coating that was added from the beginning. Yes, so let's go back to the basics. Why do we need a pre-treatment or a first step treatment? Well, normally or often you want a clean surface, and maybe you're safe with that. That's the only step, but often you need a clean surface to prepare it for the next layer of coating or treatment you want to do. And to secure that, you need a clean surface. And at the next step, then prepare for the next layer and secure then the adhesion to the next layer also. And with that also comes a better corrosion protection if you have a metal as a substrate. But as I said, also some of the methods you also can use for post-processing, and then you have your component clean again, so to say. So it's also a type of cleaning. And why we want to use the dry methods I already explained. So let's have a look at laser treatment as a pre-treatment that we can use before adhesive bonding or painting, before brazing, welding, or varnishing. Also use it, it's a coarse method, so you can use it for decoating. And traditionally, you probably know also labeling and marking of your products, or cleaning of molds, for example. Yeah, it's a small movie of showing laser treatment of this cleaning of dollies, fast and efficient process. Go. Yeah, that's true. To get rid of the Exactly. No, exactly. Yeah. So can be used to clean, to structure a surface, to improve then the wettability. If you have a microstructure that makes your water or coating, for example, wet better on the surface. Remove oxide layers, as mentioned then, and improve bonding. So, and then the effect, of course, varies with what type of laser you use. There are quite a few different equipments on the market, of course, and process parameters, what material you have, what substrate material that is you want to treat. But it's rapid, robust, close to the surface, sustainable in a way. Then you need your light source or the laser source. So energy is what you need, and no need of chemicals, and it's also automated and well controlled, which can also be a drawback, of course, because yeah, if your substrates or components varies too much, then it takes time to reprogram and all that. So it's always easy if you have a flat surface and you can just run the same way all the time. So it can also be a drawback. If you want to do, as I said, to create a microstructure or a certain structure, you have a well controlled process. It's will be the same every time you do it, very precise, compared to a blasted surface. Beware of the scales here; they're not the same. But here you have a structure, but it's homogeneous, and then a blasting surface is more irregular and also increase the surface area, but in a more unstructured way. And the reference was looked from the beginning. Yeah, some examples. And as Staffan said, please feel free to interrupt. Let's have a dialogue. We have a laser at RISE in Mölndal. It's an ND-YAG with 50 watts. Yeah, just some data that you will get the presentation later. So it's good to know. But that's the equipment used for the examples on the previous slides. And what do we? One example of a research project that is going on now, connected or where we work with laser, is laser texturing before thermal spraying, just to give an idea. And here we look at the laser possibilities to use laser instead of grit blasting process before thermal spray. So thermal spraying is the next coating layer, so to say. When you have grit blasting, you have several process steps. You clean your component, do masking, grit blasting, and then you have to get rid of the grits, demask, and then you can do your thermal spray. And then we look at is it possible to replace all these steps with the laser texturing. Yeah, and it's a project together with Högskolan Väst, Aselio, Teneco, Leax, and IKEA, Agaria, and Scandinavia. So let's continue with plasma. What is that then? Back to basics again. So yes, it's the fourth state of matter. You have your solid. You increase the temperature, you have liquid. Increase the temperature even more, you have gas. And then when you have a high temperature or high energy, you can ionize your gas, and then you get a plasma. And that is can be used then. It's a powerful media, I guess you can say. I forgot to tell you. So the picture to the right there is a plasma chamber, so low pressure plasma. Then you create a plasma in a chamber. Looks like a microwave, more or less. At least the lab version. There are large ones as well. And then you can put the component there, and then the plasma. You can treat whole components or panels, so to say. But it's a batch-wise process. And if you cannot use that or want a more online process, then you can use, there are atmospheric plasma, and then the plasma is formed within this nozzle, and the process gas then is air, so the air is ionized within the nozzle, and then you use pressure, how do you say, an air pressure that blows the plasma on the surface, and then you have a robot that will treat your surface. And then, since it's high voltage electrodes, the ionized gas, with this ionized gas, it's can even break the covalent bonds on the surface. So, for example, if you have plastic material of some kind, or you have then organic substrates, and then you can break the bonds and make it more willing to how to say, react with the next layer, so to say. If you have it then a coating, then you get a better bonding to that that layer. As with laser, this is then more you program your process, so you need to keep track of the distance, which is quite critical. From 10 millimeters up to 30 is typical numbers for the ones we use, and if you go too far away, then you don't have the effect of the surface. So the distance to the from the substrate to the nozzle, and then the speed, of course. And here there are various types of plasma nozzles and shapes, and so you can you can make a tailor-made for your products or processes. So what do you get? Yes, for example, you can improve the paint adhesion. And how is that made then? As I said, we can measure it, or have an indication at least, with measuring the contact angle. So we have polypropylene as a substrate, as is then the contact angle of 90. Compare it with if you clean the surface with isopropanol, somewhat lower contact angle. You want a low contact angle to get good wetting of the surface. But if you treat then with the plasma, you have a lower contact angle, and then from the contact angle you can calculate the surface energy, which you want to increase to get the good adhesion. So normally with polypropylene and other plastics, you are around 25, 30, 35 millinewtons per meters, and then you can put it up until 60 or 70 with the plasma treatment. And the polar contribution there is a measure of the polar part of the surface energy, is also an indication how the bonding to polar liquids are. So for example, water, you get better bonding to waterborne products than if you have the polar contribution. But that's let's have a separate seminar about contact angles and so on. I just want to show also improved bonding how it can look if you do this. You glue a dolly to the surface, and then the polypropylene as is. Here you see the surface, the polypropylene surface is black, and then you pull a pressure, and then the coating gets off, and an illustrative picture to the right there, you get the failure in the substrate instead. So the gray, can I show here? No, I can't. The gray part is the subplastic, so the failure is in the plastic substrate failure. Yes, and we have done quite a lot of work with plasma treatment at RISE, together with both within the cluster and other activities, and an ongoing project is Apply, where we look more on the implementation part. How can you simulate or how can you improve the robot programming and simulate the plasma process to implement it in your process. So we've done a lot of measurements, and together with Fraunhofer Chalmers, that do a simulation software. Input our measurements are input to them, and then we can, so you can get out the process time and or expected process time for a plasma treatment for a few of different plasma equipment. We will skip that. So I mentioned in the beginning then the winning of using dry processes compared to wet. We have done some smaller studies here. Then it's not in process baths, but if you compare with the cleaning manually with a cloth with ethanol compared to using plasma of the type that was on the previous picture. So 114 times higher CO2 equivalents when using the ethanol solvent. And case 2 with the isopropanol, and then using a sandpaper for grinding, you also have 34 times less CO2 equivalent. So this is some examples, but there are so much more to do in this field to compare. Let's see, 1140. Let's take this really quickly. But what we have seen with plasma is that you can use it for a broad variety of materials and applications. It improves the wettability, bonding strength, some cleaning effect also, but it's not so strong. But some of the, you have the air pressure that you can get rid of some particles if they are not too well binded to the surface. But it's not as powerful as a laser treatment, of course. You need to adjust the plasma parameters with your material, so you don't have exactly the same effect with polypropylene plastic as with PET, for example, or with metal. You have to adjust with the material. And what I didn't mention before is that the activation effect you get with the plasma, it drops with time and storage conditions. So with a high temperature and high humidity, then you drop the effect more quicker than if you have a room temperature and low humidity.
How quick is it? Minutes or hours?
No, more days. But so we have done some investigations of then 1 day, 2 day. You measure after 1 day, 2 day, and 1 week. It's not that it drops completely, but yeah, and it's also different for different substrate materials, how it happens. So let's go on to the next one, flame treatment. It should not look like this, but sometimes you have the feeling that it's really what can happen when you have your flame that is several centimeters in open air. Hot flame pretreatment here mounted on a robot, ready to treat plastic components. With the hot flame, you get oxidation, and you can evaporate contamination on the surface, of course. And then also you increase the polar groups on the surface, and in the same case as with plasma, then you get a better wettability and bonding to coating or next step. And flaming you can use for various types of applications, consumer goods, films, flexible packaging. Yeah, not too thin films, but then you have to be careful, probably. You don't have too much energy in automotive, in textiles, and also medical device. Some examples. Let's see, it's always good to see it. With quite a few centimeters. It doesn't always look like this, but this is one example. And as for plasma, you also have various types of nozzles and how they are shaped and formed, and that is to tailor made it for your application. So parameters in flaming then is the energy and the size of the flame, both wide and width and deep. You have a mix of air and gas. You have to control your distance to the substrate from the burner. And of course, you can play with the process speed and the burner shape and configuration. And you need a gas, normally propane or natural gas, to run the flame process. The last dry pretreatment we're gonna show is then CO2 blasting. Here there are also various types, but then you blast with CO2 pellets that can be formed either by compressing dry ice snow. So then you have the pellets as one the source, so to say, or you use liquid CO2, and then the pellets is formed within the nozzle itself. So I would say maybe it's more precise and homogeneous. Here you can see in the picture, the lower picture. And application areas for CO2 blasting, food processing equipment. You can use it for quite sensitive substrates, even art objects, and in electronics, semiconductors, medical device, but also it can also be quite coarse. So you can, if you have one type of CO2 blasting, you can also use it for decoating, so to say, to take away coatings. So it's very flexible in that perspective. And you don't get any waste, so to say, because the ice sublimates on the surface, and then you have a dry surface directly after. some risks. Carbon dioxide is toxic, so you need good ventilation. And it's quite loud also, so ear protection and as normal, clear the area. And that is, of course, for all these methods, you cannot stand too close, so to say. Actually, we had the one more example. It was the steam cleaning.
Sorry, do you have CO2 blasting at RISE?
No, the trials we have done is with rented equipment, so to say. So we have done trials, but it's not. We have our own equipment, but it's on the wish list, so to say. Steam cleaning we are not so experienced with, but it's also a flexible method. Various industries from food to automotive machinery, quite gentle cleaning. You have your steam, even if it's 180 degrees, it's not that your surface will get 180 degrees, but for some applications it might be a good alternative. Don't know if we want to fill in something. Nej.
You can clean your shoes also.
But I'm probably over time. So we've tried to summarize a bit and get an overview of the dry pretreatments. So for what you need as an input, so to say, it's power. Should be also on the CO2 blasting. It's for all the methods needs power, and for CO2 for the CO2 blasting, gas for the flame treatment, and for the plasma only compressed air. Waste-wise, compared to then the wet or cleaning methods with water or solvents, you don't get any waste. If you, of course, the contaminations or the things that you get rid of from the surface, you need to take care of. So that's a type of waste, but it's not that you need to collect more than in the ventilation, depending on the process. Work environment, and we have some pros and cons with the different methods. And we try to include also a cost column here, but that is always difficult because it depends, of course. I mean, for example, both for plasma and laser, it's the investment cost is quite high, but then the running cost, the process cost is then considerably quite low. But this is something we will continue working with, and we want to, there are a lot of things that you need to be, if you want to compare these processes to other more traditional or methods that is used today, and especially then look at the sustainability and how they stand there compared to each other. What is more or less better or worse to use? Try to find good ways to calculate that, and that is one area where we want to continue to work, and where we have a lot of discussions with the start in the surface treatment cluster companies, but also with others, of course. Yes. Questions was my next, and I have to look at since I am the time manager, that's not good. No, it should be someone else when I speak. 11:52.